Okay, thanks, Pat. Yeah, so my name is Andrei Mesinger, and I'll talk to you today about reionization and specifically about some tools which I believe will be useful in interpretation of present and upcoming observations of the Reionization epoch. So first, this is a schematic of cosmic history brought to you by some NASA PR people, as these instruments would seem to indicate. But starting from the Big Bang, obviously you have inflation, and then we think rare combination happens about a redshift of about 1100. Cold dark matter collapses, baryons collapse into halos, and sometime around redshift of 30, simulations seem to think that we get the dawn of the first astrophysical objects, the first stars, maybe the first black holes that light up the universe. And then eventually we think by a redshift of 6 that the light from these and subsequent generation of sources reionizes the universe. And so this is my research is focused on understanding this so-called dark ages and reionization epoch thus far. So first, let me show you the first and perhaps most popular reionization result that came out from the Sloan quasars. This is an updated version of result that came out in earlier 2004, 2003. And it has a similar trends as shown in that data. These are spectra from Sloan quasars in increasing redshift as you go higher. Here you see the Lyman alpha emission line. And photons that are blueward of Lyman alpha, there's a region of transmission because the quasar ionizes a region around it, and I'll go into that more in depth. But then blueward, you get strong resonant absorption in the IgM, even from residual neutral hydrogen, but you still get some signal, the Lyman alpha forest. And then as you go higher in increasing redshift, you get less and less flux. And if you plot the Gump-Peterson optical depth as a result of these neutral patches, you see a deviation from the trend at high redshifts. And this jump has often been interpreted as maybe evidence for reionization. It's not immediately obvious that this is how significant this is, because again, what you're seeing is flux, or e to the minus tau, and what you're after is the neutral fraction, which is proportionate to tau, and so getting some kind of effective optical depth from your flux measurement is actually highly sensitive to your assumed density distribution, and it's not clear that the density distributions that are assumed are that accurate enough for this task. But clearly it's a stimulating result, and we asked ourselves, can we maybe improve on this? And so I will talk about that shortly. Here are, let me talk about the current reionization constraints at redshift 6 or 7. We have recently the 3-year WMAP data detected the optical depth of electron scattering, which they attribute to reionization. If you assume some simple step function model, reionization would happen at redshift 10. The problem is that this is an integrated measurement, and so it doesn't really tell you anything about reionization history. It just gives you an integrated measurement, and it still has pretty large error bars. So even that is hard to pin down. What I just mentioned, the Lyman alpha forest in the Gump-Peterson troughs of the quasars, the fan result, they predict a neutral fraction of greater than 10 to the minus 3 in the line of sight to 2 quasars. And the recent result by Becker where they actually used a different density distribution, a log normal distribution, which doesn't seem to match simulations, but nonetheless, they claim that using this, they get no accelerated evolution. There's a bit of a sleight of hand there because they are more sensitive to their continuum fitting, and it's not clear that they do such a great job at that. But nevertheless, I mean, both of these results are highly dependent on the density distribution, and so it's one shouldn't overinterpret these. The thing to get from them is that there are large sideline to sideline scatters to different quasars, and I think that's an important point. And they, again, both assume a homogeneous background, and I'll get to that later in the talk, too. The second, probably, claim in the literature of significant neutral hydrogen and high redshifts came from these arguments of the size of the proximity regions done originally by White and Loeb. And basically, the claim goes is that the quasar blows out and ionizes a region around itself, and the size of that region tells you something about the neutral fraction that the quasar was embedded in, given the quasar lifetime and an ionizing luminosity. Obviously, this kind of estimates are very sensitive to these parameters, which are very poorly constrained at the moment. So Fan proposed the alternate method where you just look at the evolution in the size as a function of redshift, and they get roughly 10 to the minus 3 with large error bars. Again, the main problem with this is that it's model dependent, as I said, but what we originally complained about is that you can't actually directly read sizes of ionized regions from the spectra. Yes, you get transmission falls off here, but the residual absorption of resonant absorption of the residual neutral hydrogen inside the ionized regions can wipe out your flux by themselves. You don't need to hit some kind of neutral wall or increase neutral IgM to wipe out your flux. So this has been subsequently analyzed in great detail using simulations. And so it doesn't seem like these constraints are of great statistical significance. Other constraints come from using Lyman alpha emitters. And the first, it seemed that the number density of these sources can maybe yield constraints on your neutral fraction. And for example, Malhotra and Rhodes gave this constraint that the neutral fraction is less than 0.3. But if you assume that these emitters lie in clustered regions, because structure formation happens in clustered biased environments, you get a slightly weaker constraint if you use an analytic model for clustering. Recently, there was a detection of some evolution in the Lyman alpha luminosity function going from redshift 5.7 to 6, straddling what 6.5 or so, straddling what are the claims of the reionization epoch. But it's mostly at the bright end tail. And also, if you look at Lyman alpha clustering, the reionization imprints clustering signature because of the bubbles and the inhomogeneity of the reionization, and that seems to yield also a constraint on your neutral fraction at redshift 6.5. There are several also uncertainties associated with this mechanism. First and foremost, that you observe some kind of luminosity, but what is inherent in the models are the mass of halos. Now, the mapping between these two is not clear. People use very simplified assumptions, and they also assume that it's a complete deterministic mapping. It's not clear whether this is a good approach, for one thing. It's very model dependent. It's very sensitive to the fact that you assume you can predict the number densities in an ionized universe or in a partially ionized universe. And particularly this bright end drop seems to be also be able to be caused not by reionization, but by just evolution in your halo mass function. And it seems that also the reionization signature shouldn't be evidenced by just a bright end drop, but actually should result in a scale-free suppression of your luminosity function. That's a result of these models. And there was a recent paper by Iliev and some of you people that disagreed with this result on clustering, that it actually has a smaller impact than McQuinn et al. Claim. Another one, Lyman alpha damping wing, and I'll focus more on these. The basic idea is that redward of your line center or of your neutral hydrogen, you still get some absorption because you're in the wings of the Lyman alpha absorption cross-section. And so that has a specific shape. And if you can model that shape of absorption in the spectra of GRB afterglows, which are flat featureless spectra, parallel featureless spectra, you could potentially say something about the neutral fraction of the IgM. And there was a claim in the literature that it constrains the neutral fraction to less than about 0.2. However, this is very difficult to do because virtually all of these GRBs have the presence of a DLA. And in particular, this one has a very high column density DLA, something like 10 to the 21 point something. And it's very hard to disentangle the absorption profile of the DLA from the absorption profile of the neutral IgM. And also, that notwithstanding, the statistical significance is unclear because you assume in these studies that reionization is homogeneous, where in fact reionization is likely to be very patchy. And I'll, again, get more into that later. And lastly, similar detection of damping wings in quasar spectra. Here you're in a different regime because the quasar blows out large ionized regions, so you work in the ionized regions of the spectra that correspond to the ionized regions of these quasars, but you can still say something. You might still be able to say something about the neutral hydrogen in the IgM, and we did this using the fact that the flux declines very sharply, as one would expect if you had strong damping wings and a significant amount of neutral hydrogen. And if you actually model the Lyman alpha forest and try to fit parameters, and I'll again talk more about that. There are no faults with these studies to be seen. No, just kidding. I'll talk more about that later. And for some random reason, I've chosen to devote parts of the talk to these two methods. So what should we take away from this is if an optimist can look at these numbers and say, okay, so neutral fraction is about 0.1. Everything seems to kind of converge there. But that's probably not, because almost all these methods, if not all, are faulty. You should believe some more than others. And it's very important to look at the objects individually, sideline by sideline, because there should be large variations. And getting through the cosmic variance by clumping together is a daunting task. So here's the outline of my talk. I will first discuss what I just mentioned, this footprint of neutral hydrogen in the proximity regions, first through Mach spectra analysis, then modeling similar to this, but actually using the data, seeing what we can detect from that, and then through the rough trends in this particular quasar spectrum. Then I will talk about, switch gears and talk about these semi-numeric, what we're calling semi-numerical simulations, because the name is so clever. But if anybody has suggestions, I'll be happy to entertain them. But which we think are going to be very useful in the future in any of these reionization studies because they're extremely efficient. And I'll talk about that later. And applications of these methods in Lyman alpha emitter statistics and in damping studies. Okay, so let me talk about the Mach spectral analysis. So I touched on this earlier, but a toy picture of the universe during the Reionization epoch. You have a source or several sources that blow out an ionized region in a significantly neutral IgM and other sources. And your line of sight distance can be characterized by some size. And so in such a source, the spectra can be decomposed into two contributions. The absorption spectra can be in two contributions. One arising from resonance absorption, the resonance optical depth, and that corresponds to photons that redshift into Lyman alpha resonance inside the highly ionized region. And that's a very strongly fluctuating feature. The mean absorption goes up as 1 over r squared due to the flux of the source, but and it's sensitive to the Lyman alpha, the density field inside, but it's not particularly sensitive to the neutral fraction outside or the size of the region. The second component comes from this damping feature. So when you resonate, when you shift into resonance outside, your optical depth goes way up, and you're in the Gunn-Peterson trough, and at high redshifts, it's almost impossible to detect anything. But even with photons that redshift into resonance inside, they could still have some optical depth component from the neutral hydrogen in the IgM through the manner of the damping of the Lyman alpha cross section. And this is a fairly flat curve because the damping wings are fairly flat, so they integrate over large distances. And this curve is sensitive to your neutral fraction, highly sensitive to your neutral fraction, and to your size of your ionized region. So the trick is, you see the total optical depth. You see the sum of these two. Actually, you see the flux. But is it possible to, given what you see the flux, extract relevant parameters by decomposing this? So we decided to test that and create Mach spectra. We had two free parameters. The IgM neutral fraction, which roughly speaking serves to shift the damping wing component up and down. And the radius of this proximity zone or Strömgren sphere, whatever you want to call it, serves to shift this damping absorption left and right. And so what we did is we used the cosmological simulation by Reionization and extracted lines of sight through it. We select a spectrum corresponding to a random line of sight, and for each point for each choice of neutral fraction and r, the distance to the Strömgren sphere radius, we remove the resulting component of the damping wing optical depth, and what we're left with, we're hoping, is the resonance optical depth. And if we did this choice correctly, we should get something that we could predict using simulations and compare it to a template. So it turns out that this simplified model yields pretty good results. Here we have a template distribution of the resonance optical depths and the same line of sight with 3 different choices of neutral fraction and radius. And this one is the correct universe. And this one is statistically, can be proven to be statistically drawn from this distribution, whereas these two are not.
What are you subtracting?
Sorry.
You have X1 and RS, and you're subtracting. How is that a prediction for what to subtract?
So given these two components, given these two parameters, in your analytic model, you have the damping optical depth as a function of wavelength. So you have, given these two numbers, you have a curve.
So it's just
sorry. Given neutral fraction and RS, you have a well-defined curve. And you subtract that from your flux. And what you're left with, you're assuming, is the resonant optical depth.
Assuming that the rest of the universe is homogeneous.
That's something I'll get to later. This paper was done in 2004, so this was preceding the realization that the universe was reionized patchily. I don't know why that seemed to have been a recent invention, but yeah, I'll get to that later. So it turns out that with a single spectrum, you can do pretty good results. Here we have the parameter space and confidence contour, 99% confidence contours, with x's marking the true parameter combination. And in the case of a neutral universe, you can rule out a 10 to the minus 2 and a 10 to the and a neutral universe with 99% confidence contours with a single spectrum if you know the shape of the intrinsic emission. If you don't, if you add noise to it, if it's a little more messy, you need tens of spectra. So we were encouraged by this simple picture and decided to do a more detailed analysis and actually use data. In our more detailed analysis, this time we had the same free parameters, but this time we added, so actually this time we also use the lines of sight we integrate the actual optical depth through lines of sight. It doesn't actually make much of a difference in this regime because the damping is still flat, but just to be more realistic. And we also add, as a third free parameter, the ionizing luminosity of the quasar, which, varying that, serves to shift the resonance contribution up and down, right? So we have these curves wiggling and jiggling. And it's important to keep these parameters free because they can vary hugely from quasar to quasar. They're not constrained. And for example, the psi studies that I mentioned earlier just assume a deterministic mapping between all these three. And you can't do that. So the procedure here, for each point in our now three-dimensional space, is pretty much the same procedure. Well, slight difference is we construct a mock spectra using lines of sight from this cosmological simulation. And then we take the data, the Keck ESI observations of 3 high redshift quasars with redshifts greater than 6.2, and we use clean spectral regions in redward of Lyman alpha and fit a profile which we extract blueward of Lyman alpha. And then we compare these two optical depth distributions using the KS test in actual several bins, so we can keep track of wavelength information, and we see if which parameter choices match the data. And here are our fitted spectra. So we fit the spectra with a double Gaussian for the Lyman alpha line, single Gaussian for the N5 line, and a power law continuum. And the horizontal lines demarcate the regions that were used in the fitting. And here in the inlaid panels, we have zoomed in versions of the regions blueward of Lyman alpha that were used in our analysis. These are they have error bars, but the error bars in flux are extremely tiny. But through these, we generated our optical depth distributions, which we compared to simulated spectra. We remove the region immediately blueward of the Lyman alpha center, like 20 or 30 angstroms, that has the most biasing effects from the fact that the quasar lives in a biased environment. So here are the results for the 3 quasars. The blue points are 1 sigma. Well, they're not really sigma, but they're a factor of. Blue points correspond to parameter space that are within a factor of 3 from the peak likelihood. Green are within a factor of 9, and yellow are within a factor of 27. And we have the peak likelihood occurring here at these parameter choices. And these are roughly the constraints that we have on our free parameters. The neutral fraction constraint is not particularly illuminating for this one quasar. But the other parameters are actually constrained pretty tightly. And these are also pretty important parameters for understanding quasars and quasar evolution.
Co-moving H inverse megaparsecs?
Not H inverse, just co-moving megaparsecs, yes. This, unlike like I said, the size studies, we don't read this from the spectra. This is done by fitting. So this quasar actually has a more interesting constraint on the neutral fraction. It also has tight constraints on these two parameters. I'll talk more about this shaded region, which is ruled out. But the peak likelihood occurs at these three choices of parameters. And the last quasar has the same constraint on the neutral fraction with a smaller size and a weaker flux. So let's take a second to see if some of this makes sense, because yeah, you're using simulated spectra you're comparing, but do the results behave as you would expect? So it turns out the isocontours of this do behave as one would expect. For example, if you at a fixed flux threshold, this is the neutral fraction, this is the size of your ionized region. The contours go from bottom left to top right, which you would expect, because if you go to higher neutral fractions, you're shifting the dampening component up. It's the same as if you are moving your wall essentially closer. So there's a slight degeneracy in this behavior. And also, as you go from a weaker ionization flux to a stronger ionization flux, the contours move in this direction, because then essentially you're strengthening ionization flux, so you're dropping this down. So to compensate, you need to boost your dampening optical depth. So this works out okay. Secondly, there's results, which I'll get to in a minute, that are from a slightly different kind of analysis, actually agree with this analysis that I'm talking about now, which need not be the case, since this looks at the gross features and not this detailed PDF comparison. Our results on the neutral fraction do agree in relative terms with just these Gum-Peterson trough optical depth estimates. Also, the maximum likelihood of your ionization luminosity matches the strength of the continua redward in relative terms, redward of Lyman alpha, which is something you expect if your spectra doesn't do something crazy, blueward of the Lyman alpha line. And in terms of the peak likelihood values, this is the same kind of, this is not a very strong argument, but just in any case, the quasar with the smallest H2 region has the highest value of the neutral fraction and the smallest ionizing emissivity, which you would expect if you're embedded in a more neutral IgM and you're weaker, you're going to have a smaller bubble surrounding you. So let's see where the constraints from this come from. Here are the PDFs. This is the optical depth. These are the PDFs. For the X's are for 3 different bins in one of these quasar spectra. So the X's demarcate what we extracted from the data, from the actual observed Keck spectra. And the lines correspond to several different choices of parameter space. The best fit model is shown in the blue solid line, 29 megaparsec, neutral universe, and ionizing emissivity of about 10 to the 57 ionizing photons per second. And so we see that you get different constraints in different spectral regions. So for example, the closer you are to the quasar, the less the damping wing really matters, and the more the flux matters. This purple curve is the curve that has a different ionizing emissivity. And so you have more statistical weight for different things in different regions, which is why we're able to tightly constrain all three of our free parameter choices. Okay, so let me talk about this particular sight line. And this quasar actually has something very interesting, which the others don't really exhibit. And that's the fact that here you have the flux in Lyman alpha as a function of redshift. The quasar is somewhere here. And here you have the flux in Lyman beta in the same function of redshift. So there should be points here. I don't know why they went out. But until you get to this point, there are fluxes in both Lyman alpha and Lyman beta. But then you get into this interesting region in here, where your Lyman alpha flux seems to drop, but you still have flux in Lyman beta. And then you get to here, and you don't have flux in either. So because Lyman beta is less sensitive to Lyman alpha absorption than Lyman alpha, Lyman beta is less sensitive, you actually can say something about the evolution of your Lyman alpha optical depth by looking in both spectral regions. And roughly speaking, these numbers depend on your flux detection limits and your density field to some extent. But roughly speaking, this region, because there's flux in both Lyman alpha and Lyman beta, in this region you expect your optical depth to be less than about 6 for this instrument. In this intermediate region now, because you don't have Lyman alpha flux, but you have Lyman beta flux, you expect your Lyman alpha optical depth to be somewhere between 6 and 11. And now here, where you don't have flux in either, you expect it to be greater than 11. So we said, but can we just model this rough evolution using our same three parameters? Oh, sorry, I forgot that. So faulty pixel is something that doesn't behave this way. So you can, that is outside of these bounds. So we model this behavior, but we also, to be conservative, we allow 2 pixels in each region to go outside of our bounds set by this behavior that we see in the observed spectra.
So this is out of how many pixels?
In each region, there are about 8 pixels. 7 or 8. Right? Yeah, that's about right, actually. So this procedure also is able to constrain the 3 parameters, even though it's a different method than the one I described earlier. And here we see a different representation. This is the histogram of the number of lines of sight that pass our criteria. And here you see the neutral fraction and the size of the ionized bubble, and the height corresponds to the number, obviously, line of sight that pass it. And you see that the distributions are peaked here at a neutral universe with this size. And also, you constrain the ionizing luminosity. So if you want to put several panels together, you could see the thing go down. And interestingly enough, these 2 numbers agree incredibly well with the other analysis. This one is a little bit lower than is predicted by the previous analysis, and that's because we focus on the region close to the edge of the Strömgren sphere, whereas we include more intermediate regions in the previous analysis that are more sensitive to your ionizing luminosity. So, again, these can be useful tools. Here's a listing of, I'm not going to go through all these numbers, but here's a listing of the constraints that we obtain from these 3 quasars. There seems to be evidence for neutral hydrogen along at least 2 lines of sight, but one of the lines of sight, as you saw, was completely unconstrained. So we reproduce this result of fluctuation between different lines of sight. The spectra do look different. This is also, people overlook this, but this is actually the first detection of the boundary of a cosmological H2 region. Because again, as I said, you can't just read it off the spectra. You need to actually model the evolution because the resonant absorption can give you a false boundary, and depending on what your detection threshold of your instrument is. So with this modeling, we were able to detect this boundary of this H2 region. You can use the similar technique to study topology by skewering bubbles along your line of sight that are not associated with the background quasar. And you might be able to use the sharpness of the boundary using these disparate Lyman alpha lines to constrain your quasar SCD because the harder spectra are expected to have longer boundaries, ionization fronts. Although it seems that you might need longer live sources based on this study because you only get this stretching of your ionization front boundary when you approach equilibrium, which might take 10 to the 8, 10 to the 9 years, which might be longer than the lives of these sources, which people estimate between 10 to the 6 and 10 to the 8. Okay, so let me move on now to these, what we're calling the semi-numerical simulations. So the motivation behind this is that numerically speaking, it's very, very difficult, if not impossible, to study reionization. And the reason is that these bubbles are expected to be huge, tens of co-moving megaparsecs across, and your Jeans mass in an ionized IgM is something like 10 to the 8 at redshifts of 7. So to resolve scales statistically, large enough scales to have some statistical idea of what the bubbles are doing and be able to resolve 10 to the 8 halos, you need incredible dynamical range, which is not achievable by present-day clusters. And so we decided to do a hybrid scheme, which is actually in the same kind of spirit as these other simulations, PT halos and Pinocchio, which do rely on perturbation theory to obtain halo fields, but we also extended it to, we do something different, of course, but we also generate ionization fields in similar veins, which I'll describe now. So there are two components. The halo field generator, interestingly enough, we found out after we wrote the paper that this was actually pretty similar to this peak patch formalism of Bond and Myers. You might have heard of him, but he was apparently way ahead of his time in these studies. We do it a more modern version because of the ellipsoidal collapse barriers that have been developed subsequently. What? They did ellipsoidal collapse, but they did it differently. They did it with actually manually looking at like torsion and things, whereas we use a actual threshold for collapse.
Which you can do by...
Yeah. No, I know. It's the same end result, but just using different means. Yeah. No, I agree. They did it, but they just did it. The paper comes out about this big because it's, our paper's this big, but it's the same, pretty much the same thing, yeah. So the first step is to pretty much what any simulators do, n-body simulator. You create the linear density and velocity fields, Gaussian random fields, but then you use this excursion set formalism. Basically, you filter on increasingly smaller and smaller scales, and you ask yourself, is the mean density contained inside greater than some threshold that will result in a collapsed halo? And if it is, you mark that as a halo. And then to get to Eulerian space, you adjust halo locations using linear order displacements in the Zadovich approximation. So that's how we get our halo fields. Now for the ionization fields, we do something similar. We first perturb the density field using a similar method to get a quasi nonlinear density field. And then we apply also excursion set formalism to the density field and our halo field using this kind of Furlanetto et al. Technique where you do the similar kind of filtering on progressively smaller scales, and you ask, given a certain efficiency, is the region, and counting all the halos that are collapsed inside it, is the region ionized or not? And you flag it as such. So here are the results for our halo filtering. These are mass functions at 2 different redshifts, I think 6 and 10. And the green curves are Sheth-Torman mass functions here, and the points are from our simulations. So we agree very well with the analytical Sheth-Torman model. And here is comparison with an n-body code from the Harvard group. The purple line is this is the halo power spectrum as a function of scale. The purple line is what you would get before you do the Zadovich adjustments to the halo locations. And the green dotted line, the green dashed line, is what you get after you adjust the halo locations, and the red is what they measure from their n-body codes. Now you see the green and the red are indistinguishable, pretty much. I'm sorry? The Zadovich approximation is valid in the.
What's sigma?
I don't know. I would have to look. I'm sorry.
It's less than 1 or it's close to 1?
But 1.86 by linear theory, isn't it? So only thing was filtered bigger than 1.8 or something is going to be a halo.
Yeah.
No, well,
But
the RMS segment is asking about mass scale. Well, so today, I guess, M star is like 10 to 12 or so.
I think my internet is squared, right?
but I don't actually remember what they're resolving
Those aren't
mass scale is.
These are all variables that come from mass. It's also redshift.
Yeah.
I know, well, right. Like it's just like redshift 6 or 7 or something.
8. So it's high redshifts. So again, we are actually looking into now more robustly into what regimes this simulation, this technique is applicable. Yes, I mean it doesn't. We'll see. It works in the quasi nonlinear, but we'll quantify that later.
Do you allow halos to overlap after displacement?
I'm sorry?
Do you allow halos to collide after displacement?
No, halos are treated as in the filtering. Halos have a size, and they're not allowed to overlap. And the displacements, they're treated as point sources. So you move their
So after
coordinates.
they could be overlapping.
Yes, they could. But essentially, the collapsed halo has very small actual physical size. And so here's a schematic of what you would see without adjusting halo locations. The blue corresponds to halo locations in these slices. Here's after adjusting location. You see what you would expect, the clustering signature. Some of these points get tighter, which is why you get this additional shift when you go from Lagrangian to Eulerian.
Did you compare your mass function to the real mass function?
Yeah, the mass function plot I showed here. This is to the analytic, not to the n-body code. Is that what you're asking me? No, but studies, all the simulators compare it to the analytic mass functions, and they get varying agreement here and here. You could just as easily use the Press-Schechter barrier, which is shown here, and you would get points that lie here. So it's up to you what barrier you want to choose. The bubble filtering, here's a result from radiative transfer simulation using a slightly different threshold criteria, but it's still a very good agreement with our analytic result. This is just using the halo field, not even taking into account density field, but you get very nice, you reproduce the features, obviously not perfectly, but you produce all the gross features that you see in these radiative transfer, what they call radiative transfer. I mean, they don't resolve the Jeans mass, so whatever you want to call it. But you produce these features very nicely with this scheme. And here is a movie that is good for PR purposes. This is the 21 centimeter field. Now for you simulators out there, let me just give you some numbers. This is a 250 megaparsec box, which resolves halos down to 2 times 10 to the 8 solar masses. So within a factor of 2 of your cooling scale at these redshifts. So that is unachievable in n-body codes. And this is the black is obviously also the ionization field is painted on a 500 cubed grid, which also people that do RT generally work with 250 cubed. The bubbles are the black are your bubbles progressing, and you see cosmic web structures from your perturbed density field here, and you have the 21 centimeter power spectrum. So I don't know if I have time to go to both of these, but I'll try to go through one. Recent applications of this, what I think is a powerful tool. As I touched on earlier, reionization modulates the observed Lyman alpha emitter maps. For example, this is mostly ionized universe, and this is the distribution of Lyman alpha emitters you see above a given flux threshold, or mass threshold in this case. And here is the same picture at a redshift at a neutral fraction of 0.26, and you see some halos disappear, but not very many. But then as you increase the neutral fraction, more and more halos disappear. But also, why do I have a little line there? But also, they don't disappear at random. You increase the clustering because, for example, this structure here is densely populated, and so has larger bubbles surrounding it, ionized regions surrounding it. So a lot more of these guys are still visible at higher redshifts. So you actually have an induced clustering signature from reionization. So here are the resulting optical depth distributions, also with increasing neutral fraction at several mass scales, ranging from 2 orders of magnitude in mass. The red is your highest mass and going to lower mass. So you see early on, your highest mass halos are more biased, and they sit closer to the centers of larger H2 regions. And so their damping optical depth distributions are peaked towards lower optical depth, as opposed to less and less massive halos, which more homogeneously sample your ionization structure. And the differences get smaller and smaller as you get to lower neutral fractions, because the bubbles increase, and so things sit, for all intents and purposes, close to the center anyway. So you can do this same kind of analysis that has been done before to generate luminosity functions and compare it to observations. But by now, you probably think that redshift 6 is boring. So enough with the low redshift stuff. Let me move on to higher redshifts. So what about redshift 9? So the Stark et al. Had this lensing survey where they looked behind 9 different clusters and found 6 candidate Lyman alpha emitters, which would correspond to redshifts of about 9. And they seem to be pretty genuine detections. I mean, they did follow up to look for other emission lines which would be present if there were low redshift interlopers, and they didn't find any evidence for any of these emission lines. So can we see something intelligent based on this, assuming that they're genuine? Okay. Now, again, if you do these constraints based on number density, you have to assume, so far we've been working in the clean regime of just mass, but you have to assume some kind of mapping when you start comparing with observations from your halo mass to luminosity, which is very unknown, poorly known. So why don't we span some allowed range and see what we can get? Here is one of these simple maps from luminosity to halo to halo mass, and you have it depends on your parameters such as your efficiency of ionizing photons per stellar mass, your fraction of gas in stars, your time scale for star formation, and the fraction of photons that get absorbed, that don't get absorbed resonantly. So basically, why don't we mess with this factor and see what we can get using realistic numbers? So I'm not going to go through all the numbers here, but our first relation involves using the same numbers that several groups have done at redshift 6, 5.7 or something, which seem to fit luminosity functions decently in that regime, using efficiencies corresponding to pop2 stars. This translates roughly to 0.24 ionizing photons per hydrogen atom. Other relation is a little bit more crazy because you start moving into pop3 stars, and which boosts your efficiency, so you get 3.1 ionizing photons per atom. I should mention that these constraints really can only be used to set upper limits on the neutral fraction, because you don't understand the physics well enough to say anything better, but you do have a hard limit of using up almost all the gas that you have and cranking up your efficiencies and transmissions to set upper limits. And then you can do maximally conservative, but just like I said, using all the gas and cranking up the numbers, but using pop2 star efficiencies, and then just going all out and just completely using every single baryon in the halos and the stars that are pop3 stars, which is very unrealistic and gives you unrealistic ionizing photons per atom, which should have reionized the universe already at this point, but just to see what you get. And here are the resulting, so here this is in terms of mass, and we've done the mappings from your luminosity to the mass to map it to compare with our mass functions. And these are the four relations going from 1 to 4. Again, 4 is very unrealistic, but this is the absolute hard wall that you can hit. But it's unrealistic because the universe would have been reionized earlier. And these are, the black line, is for a completely ionized universe and going down into increasingly more and more neutral universes. We see that using the same parameters as redshift 6 observations completely overestimates your number density, even for a completely ionized universe. So something is going on. Either the candidates are bogus. We also estimated the cosmic variance with our simulation. This is the Poisson plus cosmic variance error bars that you see here for two different models, for two different neutral fractions. And this mapping just doesn't work. The second two are more reasonable. They're in the correct regime. So you need something to change from 6 to 9, whether in efficiencies, whether in your the nature of star formation. But even given these two conservative mappings, we're able to set a constraint on this neutral fraction that it has to be less than about 0.7. But more fundamentally, if this is genuine, this result from them, it would require, I mean, these are the mass functions at redshift 9. It would require star formation in this regime of very small halos, less than 10 to the 9 solar masses, which would be some of the smallest halos detected anywhere at any redshift. So also we looked at the counts and cell statistics to try to look at approach reionization through the reionization induced clustering. And I don't have time to go into the details, but it does seem to be a robust way of doing this, and it contains potentially more information than the more usual power spectrum approach, or the two-point correlation function, because it includes higher order correlations. And we find that it's actually, the signal is stronger than you would get from evolution in the halo mass function. And so let me just introduce this plot. This is the neutral fraction, and on this axis you have the increased likelihood of finding more than n Lyman alpha emitters in your field of view, given that the field of view has already a Lyman alpha emitter, increased with respect to an ionized universe at the same number density, so normalized at the same number density. And we see that this is for 2 or above. This is the second order term. We see that you still get, at above redshift of 5, you get over 10% increased likelihood of finding more than one Lyman alpha emitter if in a cell that already has a Lyman alpha emitter. So it's reionization-induced clustering. And this is the same for n equals 3, so more than 2 Lyman alpha. So there's still information in those things. And we see that this is the number of cells that already contain sources that you would need to constrain reionization at 2 or 3 sigma. And you could see that you could get a 3 sigma detection at above redshift of 5 using some normal standard fields, using less than 100 or so fields, which is pretty optimistic, because you could construct a survey strategy where you have a shallow observation, and then you do deep follow-up surrounding your bright sources to look for a clustering signature. Okay, so I don't have time to go through this. If you have questions about it, you can ask me during the questions. Let me just end on my conclusions. So we extracted these parameters, but then I skip through the part where we actually show that reionization, if you do patchy modeling of reionization, you actually introduce significant scatter in these kind of analysis. So you really need to update these works and do more realistic patchy reionization modeling. The numerical simulation can be a useful tool for various things. And these Lyman alpha 9 emitters at Lyman alpha 9 do seem to apply a fairly ionized universe at redshift 9 and significant low mass star formation. Star formation and low mass halos, with the counts in cells being a very powerful probe for detecting reionization-induced clustering. And this is the kind of crux. You really should use models to interpret your data, because things aren't as simple as everybody, including us, would sometimes like you to believe. So, thank you.